Oh, so that mistake I was pointing out in that one, it was a Hessenberg QR step algorithm. Are you using it in the coding project or?
I don't think so.
Okay, yeah, because there's a different algorithm that's specifically for tridiagonal case. The one from Gallagher loan that would be better for that.
Yeah, I was
Okay.
just going through and looking at different algorithms.
Oh, okay, all right.
So that's how I coded it.
Oh, okay.
Just to verify.
Yep.
Yeah, no,
Yeah.
uh,
Okay. Yeah, all right, good enough. That this doesn't influence the assignment at all, but yeah. Okay. Well, what I'm referring to is in the text. I posted a list of mistakes on my website, but that list is not complete because there's some more recently found one that I haven't gotten around to posting yet. Algorithm 6.3.2 on page 219. So this is not an algorithm that's needed for the homework 4 coding option. This is for Hessenberg QR step, and there's a line in there that says H using MATLAB rows J and J plus 1, columns J through N is set equal to a Gibbons rotation, J transpose, and the way H is indexed is supposed to be the same on both sides of the equation. And now currently what it says is all columns of H. So that should be columns J through N. Okay. Because since we're trying to reduce H to upper triangular form, in rows J and J plus 1, anything in columns to the left, like columns 1 through J minus 1, those entries are already 0. That's why it's only necessary to focus on columns J through N. And I'm not sure what I was thinking over here, so. Okay. Now, today is the last, what I would consider a true numerical linear algebra topic that we're going to see. This is the SVD algorithm. We've seen the SVD like from chapter 4, but not how to compute it. Now that we know how to compute eigenvalues, we can use those tools for this. This is the algorithm that was developed by my advisor, Gene Golub, and William Kahan from UC Berkeley. So Golub Kahan SVD algorithm. And so it's what my advisor was best known for. I mean, he did a lot of things during his career. But developing this the year when I was born, actually. So wouldn't say it's up for a moon landing, but among the things that happened in '69, this one was pretty great and used a lot since then. And even though the algorithm has evolved a lot, there have been improvements made and so forth, but it all started with this. And Gene was so associated with the SVD that for his 60th birthday, for the cake was decorated to have the entries of a matrix on it, such that if you were to compute the singular values of the matrix and then map them to characters using the ASCII character set, it would spell out "Happy Birthday, Gene." So yeah,
that's impressive. Right?
Yeah.
Impressive.
Um,
Thought process behind that.
yeah. Yeah, and so I'm thinking like, okay, if you make a diagonal matrix that has that unsingular values, when you multiply them by orthogonal matrices on the right and left, so like U sigma V transpose, those numbers are going to be crazy. So Unfortunately, I wasn't there, to see what the actual cake was like, but, yeah, because I mean, you could have an image put onto a cake. But this was back in, 1992, so I don't think that was a thing back then, because World Wide Web didn't exist yet either. Okay, so, um, so to recap, um, we have, A is n by n. Every m by n matrix has a singular value composition. U is m by m. B is n by n. Sigma is m by n, same size as A. U would be our orthogonal matrices, and sigma is a diagonal matrix. As diagonal matrix consists of singular values, sigma 1, sigma 2, and so forth. Okay. Now, okay. Oh, what's weird? Oh, the algorithm is from 1965, not 1969. Okay. Something important to 69. Maybe 69 is when he started at Stanford. I don't know. It's significant in some way. Okay. So we're going to relate the SVD to a symmetric eigenvalue problem. And since we've just covered how to solve symmetric eigenvalue problem, we can take advantage of that for the SVD. So I'll write U as a column partition and V. Okay. And I'm going to let P be the minimum of M and N. Because this is meant for square or rectangular matrices, any kind of rectangle, doesn't matter. So P is how many singular values actually have, because that's the only diagonal entries that you can have in sigma. So what was covered last time we saw the SVD was, and you can get this from the singular value decomposition equation itself. If I take A equals U sigma V transpose, and I multiply both sides on the right by V, I get AV equals U sigma. Similarly, if I take the transpose of that equation and multiply both sides on the right by U, I also have A transpose U is equal to V sigma. Okay, so now if I look at these equations column by column, I have A Bj is equal to sigma j Uj, because what's happening here, oh wait, that should be sigma transpose, whoops. Okay, now when you take a matrix and you scale it, and you multiply, if you take a matrix and scale it by a diagonal matrix on the right, but which is what's happening in both of these cases, you're scaling the columns by the diagonal entries. Whereas if you're multiplying by a diagonal matrix on the left, it scales the rows. So that's what's happening here. A times the jth column of V is a jth column of U, but scaled by sigma j. And similar thing over here, A transpose Uj is equal to sigma j Vj, and j goes from 1 up to P that this holds. So it's kind of like a eigenvalue, eigenvector relationship, except for one thing. The vectors on both sides are different. And if you have A times a vector equals a scalar times the same vector, that's an eigenvalue, eigenvector situation. But since A changes V's to U's and A transpose changes U's to V's, what if we put these two equations together? So for example, if I take the left one and I multiply both sides by A transpose, then I have A transpose A Bj is equal to sigma j A transpose Uj, but I fill in this over here. So I'm going to end up with sigma j squared Bj. So now I do have an eigenvalue, eigenvector relationship, and A transpose A is a square matrix. This is n by n. Okay. I can do the same thing if I take this equation and multiply both sides on the left by A. Then A transpose Uj is sigma j squared Uj. So the right singular vectors are eigenvectors of A transpose A. The left singular vectors are eigenvectors of A transpose, both symmetric matrices. The eigenvalues in both cases are the singular value squared. Now, so here's one thing we could do. Get the economy size SVD. So A is still U sigma V transpose, but so A is n by n. Sigma is a square matrix of size P by P, so it's the minimum size. U would have to be M by P, and V would have to be V transpose is P by N. Okay. So here's our first attempt at an algorithm. So I go ahead and compute B equal A transpose A. And I'm going to assume right here that N is less than or equal to M, like we had in the full rank least squares problem. If that's not true, then we can work with AA transpose instead. The point is, this is a square matrix of a smaller dimension. Okay. Then what you do is use a symmetric QR algorithm on B. So now B is going to be equal to B sigma squared B transpose, because the matrix in the middle will have the singular value squared on diagonal, but that's going to be right. I need to fudge this a little bit. I'm going to take my assumption about M greater than or equal to N and move it up here. So that way my decomposition will be N, N by N, N by N. Okay. Okay. So you'll get all the singular values. squared as the eigenvalues of V. Okay. So we have most of singular value decomposition now. We have the V, and we can take the square roots of these eigenvalues to get sigma. All that's left is U, but we know how to get U. We can use the relationship AV is equal to U sigma to get U. So all we gotta do is take our eigenvectors of B that we found, multiply them all by A, and then we'll get the scaled columns of U. So all we gotta do is we just normalize the columns. All right. Actually, it's a little more elaborate than that. It's QR with column pivoting. Okay, so yeah, so that way you'll get these in the right order.
You said to get the singular values in the right order.
Yeah, so they'll actually go from largest to smallest. Okay. Okay. Yeah. And A times V, once you compute that, that will already, that its columns will be orthonormal already. But since you can't count on for sure like what order the columns of V will be in, to make sure that they're ordered correctly, you could QR column pivoting will ensure that because it'll take the column of largest magnitude, move that to the front, corresponding to the largest single value, and then whatever scrambling happened to QR column pivoting, you can apply that same scrambling to V, and now everything's in the correct order. Will it also apply to sigma?
Yeah, that makes sense.
Okay. Now, this is the economy size. Now, on the other hand, if okay, well, okay, yeah, I can call it economy size because it's U and V are not both square in this case. They're abbreviated. Now, did anyone tell me, looking at this procedure right here, suppose this assumption did not hold, suppose n was less than n. How could I tweak this in a minor way to still get the SVD? Well, something does get swapped around, but. That will help. But before that, we should tweak the first step.
Yeah, to have an A times A transpose.
Yeah, that's not the transpose.
Oh,
Okay, yeah.
yeah.
This is metric. But yeah, you are swapping something.
Yeah.
So then you'll have a matrix of smaller dimension and symmetric. And then you do symmetric QR algorithm on the change B, and that will give you U. And then you use A transpose U as V sigma to get V. Yeah. Yeah. Okay. So you might think, well, why are we still here? But there is a very good reason. Okay. Because the QR algorithm is pretty reasonable, and then the QR algorithm, the column pivoting will be quick in this case. Is because of loss of information. In the very first step in computing A transpose A or AA transpose, whichever one it is. So all floating point operations to form B entries of B. Information about A is lost due to rounding. So we like to avoid forming A transpose A or A transpose explicitly. So there's never one of those cardinal sins of numerical linear algebra. I can tell you to never explicitly compute the inverse. You also try not to compute A transpose A or A transpose. Those matrices do come up in a number of applications. But if we can, like, again, fake it till you make it, that's also a model of numerical linear algebra apparently. Or if not, it should be. So that's what we're going to do. We're going to pretend to apply the symmetric QR algorithm to A transpose A without actually computing it. Okay. So what we'll do instead, well, okay, let's revisit the symmetric QR algorithm. What is the first thing that the symmetric QR algorithm does?
The ship.
No, before that. What is the first major step in the symmetric QR algorithm? So you have some general symmetric matrix.
Reducing it to tridiagonal.
Yes, reducing it to tridiagonal form. So what we're going to do is do the following. Transformation to this form where we're applying orthogonal matrices to the left and right of A to get a matrix B, different B. I should have called something else over there. That is upper bidiagonal. Okay, because when we do that, then if we were to form this matrix, T equals B transpose B, that would be tridiagonal. Okay, but we're never going to actually form T, at least not in its entirety. These matrices U1 and V1 are products of householders. Okay.
What is that?
Oh, what?
F.
Oh, it's meaning just whatever
Okay.
non-zero entries we have.
Okay.
Yeah.
I just wanted to make sure that I didn't miss.
Oh, okay. No, I haven't defined these things. Okay. Okay. So what that means is B1 would be the transformation you'd use if you did compute A transpose A. B1 is what would perform the tridiagonal reduction. So we are still computing it, but based on using the entries of A, not A transpose A. Okay. In my notes, I never used B to refer to A transpose A. Good thing. All right. Now, having done this, yes, we could form B transpose B equal T and then do a symmetric QR algorithm on T. But again, we're still experiencing a loss of information if we do that. So we want to try to work directly on B because we're almost there. We want this to be diagonal. We're almost there. we just have to keep working on this to try to get rid of these super diagonal entries. Okay. So what we do is instead of the usual process that you were carrying on T, where you compute the QR factorization of T minus a shift, and then multiplying the factors in reverse order and adding a shift back. Here's what we do. You compute a Gibbons rotation G1. That would be first transformation that was carried out in QR factorizing T minus mu identity. Okay. Where mu is the Wilkinson shift. Okay, one thing I just realized is, okay, well, as far as figuring out the Gibbons rotation, that does require computing the first column of T. Now, I say in my notes that it requires only computing the first column of T, and that is enough to figure out. Well, we also need to shift though. To get the shift, a Wilkinson shift, we need, because the Wilkinson is based on the that lower right 2x2 block of T, you need that too. It may be possible, well, it is possible to express that in terms of these entries directly. So you could do that to get the shift. And once you have a first column in this matrix, that's enough to determine the Gibbons rotation. So G1, its job is to zero out a 2-1 entry of T minus mu identity.
Yeah, I got it.
Okay. I may have said it, but I didn't write it down. This is a Gibbons rotation. Right, because and we have a tridiagonal matrix for QR factorizing. It's going to be all Gibbons rotations. Okay. All right. Actually, I'm going to take a look at the commentary in Galb and Van Loan on this. Okay. So this would be in chapter 8 of that book. Code methods, SVD algorithm. Where is it? Okay, so okay, so for instance, in Galb and Van Loan, they express, they don't talk about explicitly forming that lower right 2x2 block. They do give it in terms of the entries of the Ds and the Fs. So, so basically you are computing it. All right.
Well, are you only computing it in like 2x2 matrices, essentially?
Yeah, so you compute, yeah, you're computing a 2x2 block just to get the shift. Okay, but yeah, I need to amend my comment here, but okay.
Yeah, what threw me when you wrote the G1 zeros part.
Oh.
But 2-1 would already be 0 because I looked over at what we have for B.
Oh,
And I was thinking
yeah.
that is.
Okay,
the wrong
yeah,
thing.
yeah. All right. Okay. Now what, so now we have this given rotation. We're not going to apply it to T because we don't want to form all of T. So then, so we're going to compute, I'll call it B1, which is our B here, and we're going to apply G1 on the right. Now, that seems rather odd, but applying this given rotation to B on the right is equivalent to because if I with B1 transpose B1, that would be equal to G1 transpose B transpose B G1. Okay, so by applying it to this given rotation to B on the right, it has the effect of forming the whole similarity transformation of T if we were to compute it. The thing going back and forth between what we actually do and what we imagine we're doing. Okay. Now, let's look at the structure of it. Because B is upper bidiagonal. And G1 is a Gibbons rotation of, and we're applying on the right, so it's of columns 1 and 2. So by rotating columns 1 and 2 of this matrix, what's going to happen? What's going to change in terms of what's 0 and non-zero? The 120 is not going to become 0 because the Gibbs rotation is based on zeroing something of T, not B. No.
Well,
Okay, so columns 1 and 2 get rotated. So because this Gibbs rotation is meant to zero out some element of a shifted T, but we're applying it to B, it's not going to make anything 0.
yeah, you're just gonna add elements. It's gonna remove 0 elements, correct?
Yeah, it's going to make something non-zero. Which entry will become non-zero?
That was such a better way to say it than I said.
Well, that's the option point.
See what?
Yes. Yeah, row 2, column 1. So now we have an unwanted non-zero entry right here. And then everything else is unaffected. Okay. All right. So we just messed up B.
Right.
Okay, so now what we'll do is apply a Givens rotation, H1, to rows 1 and 2 of B1. So that will get B2 is H1 transpose BG1. So, okay, so now that 2-1 entry becomes 0, but we're rotating rows 1 and 2. So what's going to become newly non-zero?
One, three.
What?
One, three.
1, 3, yes. Yeah, this entry right here becomes non-zero. Sound like it said 1, 2 earlier, I didn't. Oh, okay, all right.
It was a mixture between 3 and 3rd.
Oh, okay, okay. And then anything in rows further down is unaffected. Okay,
Okay. Well, wouldn't 2-1 still be non-zero?
oh, wait a minute. Oh, but, oh, this entry right here,
Yeah.
but H1 is specifically designed to zero it.
Oh,
Yeah,
okay.
yeah.
Only doing that, okay.
Okay, yeah,
That's,
yeah,
it's not.
yeah, because now we no longer care about what might be done to T. We're not faking it anymore. We're just looking at B and figuring out what to do. Okay. All right. Okay. So what should we do next to get rid of that unwanted non-zero entry we just put in there?
Rotate columns again.
Yes. So we apply another Givens rotation. I'll call G2 to columns 2 and 3 of B2. So now we have B3 is H1 transpose B, G1, G2. Oh, Hattiesburg. Okay. I gotta go notice that there too, but, okay. Now, it's rotating columns 2 and 3, so column 1 won't be affected, and then columns 4 and 5 won't be affected either. So what's gonna happen that we don't want with columns 2 and 3? Okay, so I'm rotating columns 2 and 3, so what unwanted non-zero is going to appear?
2, 3, 3, 2.
Yes, row 3, column 2. So we have 1, 2, 3, okay. This entry was made, okay, so first time. So this one is zeros. The 2-1 entry. This rotation here, zeros. Entry in row 1, column 3, but now we have that introduced, and then we have the rest of this column here. Okay, so what have we been zeroing? Well, the first transformation didn't zero anything and introduced a new non-zero. So then we zeroed out 2-1. Then we zeroed out 1-3. But now 3-2 has to be targeted. So you get the idea. So this is where I pull that, continuing this process thing again. Okay. Okay. All right, so, so really what you're doing is like, okay, you zero this out, it's gonna wind up here, then it'll wind up here, and then here, and then it's gone. You are chasing the unwanted zero out of the matrix. So, okay, so once you've gotten all the way to the bottom, you'll restore upper bidiagonal form. Okay. But
This would be a fun game, like.
yeah.
just quickly,
It's like whack-a-mole.
That's what I was thinking when you did step 3. I'm like, he was just playing whack-a-mole right now.
Yeah, yeah.
What we're gonna do.
Yeah, and then unlike whack-a-mole where it could pop up randomly, you know where it's gonna pop up and you know to go after it. Yeah. Mm. So, so because the very first rotation we performed, G1, is the first rotation that would be used in the QR factorization of P minus mu identity if we had computed it. Then we have okay. I define Q tilde to be equal to the product of all the column rotations that I need to pull this off. Let's see, so I need column rotations to get column, so first we have, well, the very first one, G2 does okay. Get something in column 3. Okay, so it's 2, 1, 1, 3. I'm trying to think, how many do I need? Oh, so it's really anything in the second super diagonal that I'm trying to get rid of. So I'm gonna need n minus 1 rotations total when I include G1 in the mix. Okay, so this orthogonal matrix is essentially equal to this Q right here. That if we had form T minus mu identity and computes QR factorization, now we've effectively computed this Q anyway. And we know it's essentially equal by the implicit Q theorem. Oh, emoted. Okay.
22nd super diagonal, and I thought that's what she was operating on, but the zeros that we're bringing is the sub-diagonal, that's why, anyways.
Yeah.
Because I thought it would be minus 2.
Oh, okay.
Non-zero is introduced.
Okay, so what we've done is we're still coming up with the correct similarity transformations that would be applied to A transpose A if we were to compute it. But now we can figure out how to do all those transformations by working only on the upper bidiagonal matrix B. Okay. So the idea is we can just carry out this process until, so what I've shown you here is how to do one implicit QR step. So we would keep going until our upper bidiagonal matrix is reduced to diagonal form. Okay. Any questions about this crazy process here? Okay. The only thing that remains to deal with is the whole decoupling issue. If you're actually doing a symmetric QO algorithm, you have this tridiagonal matrix, and you're trying to reduce the diagonal form, and you look for subdiagonal entries to become zero, and then you know that the problem decouples. But since we're not computing a tridiagonal matrix, how do we know if we have decoupling in this case? So it turns out not to be too difficult, but it's a little more work. So because the idea is what to work on, I guess what you can think of it as an unreduced upper bidiagonal matrix to avoid superfluous computation. So if any of the superdiagonal entries become zero, then we have decoupling. Okay. Now, that would be a situation like this where we have the V1, V2, V3, V4, V5 on the diagonal. And let's suppose that F2 is zero in this example. Okay, bad partition, but you get the idea. Because what happens is these off diagonal entries of T are equal to, okay. So I need to cheat here for a second. Okay, is equal to DI FI. So, yeah, so each off diagonal entry is a product of a diagonal entry and a super diagonal entry of B. So if either one of these becomes zero, you have some decoupling going on. Okay.
I equals the I.
That comes from like actually carrying out the matrix multiplication. That's the matrix multiplication. Like here, this is B transpose and this is B. So I want the 2-1 entry, for instance, I do F1 D1 plus D2 times 0. Yeah. All right, so if a super diagonal entry happens, then immediately there's some decoupling. So we could like focus on this part or the other part. If any diagonal entry becomes 0, there's also decoupling, but it takes a little more work to do to take advantage of it. So I'll return to this example. Let's suppose I have, suppose D3 turns out to be 0. But the super diagonal entries, suppose they're all still non-zero. Okay. Yeah, so at this point, we don't really have an obvious block diagonal structure. So what you can do is Okay,
We get one when we did, the next rotation. If we switch columns 3 and 4,
but yes, so what do you have to do, and I have this in my notes, but not in detail. You can perform gibbous rotations to zero out either an entire row or entire column of this. So for example, okay. If I do so for example, but what you need to get careful about is to make sure we preserve the eigenvalues. If you apply, oh, wait, we're not trying to preserve eigenvalues. We're allowed to apply Gibbons rotations on either the left or the right, because we're just accumulating transforms in U and V. Okay, so okay. So let's suppose if I do a Gibbons rotation, like on these two columns, to zero out F2. Okay, but then we have a non-zero entry down here. Okay, as I'm rotating, if I'm using columns 3 and 4. Okay, then I'm gonna have something over here. That might not be the best idea. Because you're gonna get a new non-zero entry no matter what. Okay. That's really what we call swap. Hold on. Okay. Zero. Okay. Okay. So we have that. 4.3, 4, 5, 6. Okay. So here, for instance, I made D3 turned out to be 0. Okay. All right, hold on. What do you suggest? Doing only row rotations. Okay. So in this example, rotating okay, so so this is an example of Galvin loan. D3 turns out to be 0, just like what I have. And then doing some rotations with revolving row 3 to zero out the entire third row. Okay. So what you can do, for instance, is do this rotation. Okay. So first 2 rows will stay untouched. In the third row, that's still 0, and then I do a Gibbons rotation that'll wipe that out. F3. But now we're going to get a new non-zero. I'll call this G3. Okay. And then what you can do is now do a Gibbons rotation with row 3 and row 5 to wipe that out. Now the entire third row is 0. And you get decoupling like that. Yeah.
Different case.
Oh, sure. Yeah, because what this means is certainly this matrix is singular. So you're gonna get a 0 singular value. Oh, well, it happens. What this means is this is the exception. Most of the time, certainly if your matrix is non-singular, the only way you're gonna get decoupling is through this case right here. Sorry, what? Yeah, so first I did rotating rows 3 and 4, 3 and 5. Yeah.
3 and 4, then 3 and 4 again, and then 3 and 5.
Oh,
Actually, not. Yeah.
Okay, yes. Okay, yep. Okay. Okay, so this works well in most cases. One exception they have is suppose the very last diagonal entry is 0. Then you can use column rotation to 0 the entire last column. Okay, so one way or another, decoupling happens. If anything becomes 0, you just might need to do some givens to take advantage of it. Okay. All right, so, and that's it really. So whatever transformations you apply on the left, that gives you U, and accumulating all transformations on the right give you B. But diagonal matrix you've reduced A to is sigma. Well, except that the singular values may not be in the right order, but then you can do some permutation matrix to deal with that. Okay. The only thing we're pointing out is I think I didn't really cover this when I did symmetric eigenvalue problem. So there are certain results about sensitivity of eigenvalues for a symmetric eigenvalue problem. Like for instance, Gershgorn circle theorem and all that. So because the SVD and the symmetric eigenvalue problem are so closely related, it's possible to get results, theoretical results about the sensitivity of singular values in terms of based on results about the sensitivity of eigenvalues in the symmetric case. So whatever theorems are about that, that's how they're proved basically. Okay. Alrighty. Yeah, that's all I got. Oh. Okay, now. Any questions about anything? More issues? What? Okay. All right. Okay, so the only thing left is next week. Yep, have a good weekend too. Next week I'll tiptoe into statistical learning, and then we call it a semester. Oh, it's the basics of statistical learning for next week. Yeah, very basic stuff. Yeah. It's all even I can handle right now.